We're going to talk about graphing rational functions. So graphs of rational functions can look in a variety of ways. However, the big thing is, and if you look at the three examples that I've given you, is that we have points of discontinuity. For example, there's gaps in the graph. It's not one smooth consecutive curve or one smooth line. We will have different breaking points. This is because we have excluded values that we have already found. So we will have both vertical and horizontal asymptotes at time, and sometimes something called an oblique or slant asymptote. However, rational functions are usually made up of different branches. So in the first example, we can see there are two curves or two branches with a gap in between the two. On the second example, we have three different curves with multiple asymptotes. And on the third example, we have two different curves, and here we have that oblique or slant asymptote. So what you need to memorize is how we find these asymptotes, and then the curves are pretty easy to find after that. So our focus is going to be on those points of discontinuity or where those asymptotes are. All right, so again, some properties, there are two or more branches. These branches approach lines called asymptotes, and as we learned about asymptotes, those are places where the graph is undefined or not defined. Apologize, it says note, but not defined. And then other times we might have something called a hole instead of an asymptote. So let's talk about how we find these, and then we'll actually look at examples. So to find a vertical asymptote, what you're going to do is factor the denominator, okay, which we have been doing lots of. So factor your denominator and determine what makes that denominator 0. That's what we've been doing for our excluded values in our domain. Those are our vertical asymptotes, okay? If that value is also factored in the numerator, then instead of a vertical asymptote, we have a hole. All right, so for example, if I factor something and I get x plus 5 over x plus 7, okay, that vertical asymptote would be at x equals negative 7. However, if I had something like the following, if I had something that said x plus 5 over x plus 7 and x plus 5, I will still have a vertical asymptote at x equals negative 7, but also notice the factor of x plus 5 is on top and bottom. So I will not have a vertical asymptote at x equals negative 5. I will have a hole at x equals negative 5. Okay, and we'll go through more examples of that so that you can clearly see. But to find vertical asymptotes, we focus on that denominator. If there's a same factor in the numerator, then that creates a hole. Okay? Horizontal asymptotes, there are 3 rules, and we focus on the powers of the terms. So if the power in the denominator is larger, then we will always have a horizontal asymptote on the x-axis, y equals 0. If the power in the denominator and numerator are the same, then we divide the leading coefficients of the numerator and denominator. Whatever value you get, that's where your horizontal asymptote is. So if we divide and we get 3, then my asymptote is at y equals 3. Now, if the power in the numerator is larger than in the denominator, we do not have a horizontal asymptote at all, and instead we have a slant or oblique asymptote. And we'll go into that in more detail. But a slant asymptote is in the form of y equals mx plus b, and we find that by using long or synthetic division. Okay, so we are going to reference back to this first page of notes quite often as we do our graphs. So when we are graphing, we need to make sure to find our vertical asymptotes or holes, find our horizontal asymptotes, and then we're going to make a table of values with test points, and we base those around our vertical asymptotes. And then often we'll ask to determine the domain and range or other key points. So let's look at this first graph that's given. We're going to identify key parts so that you understand what these different vocab words mean. So in this case here, our hole. Notice this open circle here, okay? Right here is the hole. So we have a hole at the ordered pair of -8, 6. Okay, so that means at -8, we had some factor of x plus 8 and x plus 8 on top and bottom, because that gives us a -8. Now, part B says find our x-intercept. So our x-intercept is where we cross our x-axis. Apologize for the bell. We're just crossing once, and that is right here at the ordered pair 4, 0. Our y-intercept is where we cross the y-axis. So I look at my y-axis, and I'm just crossing it once, and that is at the ordered pair 0, -6. Part D, our vertical asymptote. Vertical is up and down, right? So if we look at x equals -2 is my vertical asymptote. Please make sure you're writing that as an equation. Don't just say -2. Okay, so up and down, the asymptote is at x equals -2. And then E, our horizontal asymptote, is going to be up at y equals +3. There are no slant asymptotes, right? There's no diagonal dotted lines, so there's no slant asymptotes. So those are some of the key pieces. That means we have 3 areas of discontinuity. At the whole, there's a gap, and then at my different asymptotes, there's also gaps. Okay? So let's actually go ahead and do a graph. We'll start pretty basic. In this first one here, the first thing we're going to do is we're going to find our vertical asymptotes. And the way we do that is we make sure to factor the numerator and the denominator. Good news is nothing needs to be factored. So now what I look at is I see, are there any common factors up top and on bottom? No. So that means no holes. For our vertical asymptote, though, we will have one, and we set our denominator to 0. That gives me x equals -2. So there's the vertical asymptote. And if you want to sketch things as you go, you can. So I'm just going to put a dotted vertical line at -2. Now we're going to find our horizontal asymptote. So to find our horizontal asymptote, it's all about power. So I'm going to scroll back up to the bottom of the first page of notes. And what we want to determine is if the power is larger in the denominator, if it's larger in the numerator, or if it's the same. And on our example, we don't have an x in the numerator at all. So we have x to the 0 up top and then x to the first on the bottom. So that means the power is larger in my denominator. So that would be our first example right here. If the power in the denominator is larger than in the numerator, my asymptote will be at y equals 0. So there we have it. Our horizontal asymptote will be at y equals 0. So now I will sketch that. That's right on the x-axis. Okay. So now that we have that, I'm going to make a table of values. And my table of values is going to be based upon the vertical asymptote. We just have one, so that's really nice. That vertical asymptote is at -2. We don't have an ordered pair. It's undefined at -2. Notice that I put that in the middle of my graph because just like when we graphed exponentials or logarithms or quadratics, we base our graph around some key points. We test points to the left and to the right of it. So I'm going to plug in values of -3 and -4 and -1 and 0. You can absolutely do more points, but certainly 2 of them will start to give you the right idea. Just recall that we have branches and curves, so you're never going to connect a line at all with those. Okay, so now that we have that, let's actually plug those values in. Okay, so when I plug in -4, and you can do that out on the side or however you'd like to do it, but this would be saying 3 over -4 plus 2. That gives me 3 over -2. So we get -3/2. Okay, Now let's do negative 3. This would be 3 over negative 3 plus 2. This would give me 3 over negative 1, which is negative 3. Let's plug in negative 1. That would be 3 over negative 1 plus 2. That would give me 3 over 1, which is positive 3. And then if I plug in 0, we get 3 over 0 plus 2, which is 3/2. Okay, so again, just finding some test points. I'm going to erase my scratch work so that we have more room for analyzing afterwards. So now I'm going to plot those points. Okay, so we'll plot the ordered pair of negative 4, negative 3 halves. So negative 4, negative 3/2 is negative 1.5. We have negative 3, negative 3. We have negative 1, 3, and 0, 1.5. So if you notice those points, I'm just going to make it a little bit bigger. Remember that we cannot pass through asymptotes and that rational functions are branches and curves. So you can do more points if you want, but please understand we're not just connecting a line through my dots. What happens on this bottom part is that we have a curve forming. I can't pass my asymptote, so it approaches that y equals 0, and then it also approaches that x equals negative 2. So there's one branch. Same thing with the branch up in the positive axis area. Okay, I approach those asymptotes and I am a curve. And there's your graph. Okay, now sometimes it may ask you for what your y-intercept are and your x-intercept. So if we talk about that, our y-intercept is where we cross our y-axis, which we found right here, right? When you plug in 0 for x as your y-intercept. So that is the ordered pair 0, 3/2. And then our x-intercept is where I cross the x-axis. Well, there's an asymptote there. It's saying never cross that. So in this case, our x-intercept is none. Okay, so there is our first graph. I'm going to do 2 more with you and have you try one on your own. So the one that I'm going to have you try is going to be number 2, okay? It's going to be pretty similar to what we just did. However, you're going to have 2 vertical asymptotes. So therefore, when you make your table of values, you're going to have 2 key points that you're going to base values off, okay? And as a hint, your graph should look something similar to example 2 of these 3 graphs up here. Okay, so attempt number 2, I'm going to now do 3 and 4 with you since those are slightly different.